Evening, sir.
Can you hear my voice?
Yes, sir.
Hello? Hello? Can you hear my voice? Okay, so good evening once again. So this meeting, our discussions would be focused on analysis of two-dimensional frames. No? So the last time we met, we discussed two-dimensional beams. So karon two-dimensional frames ta. And after that, we're going to discuss analysis of grids, then analysis of three-dimensional trusses, then finally analysis of three-dimensional frames. So it's like we have three topics, no? Four topics including this ang nabilin sa atong matrix analysis of structures. So let me now share my screen. By the way, nag-post na ko sa atong canvas sa assignment na to for the two-dimensional frames. Okay, so makita rin ninyo ang screen?
Yes.
Sige. So last meeting, ako lang i-confirm, no? So last meeting, ang atong topic, two-dimensional beams, right? Was it two-dimensional beams? Okay. So karon two-dimensional frames ta naara gyapon ni sa chapter 3 sa atong textbook, no? Kang matrix analysis of structures by Robert Sianet. So as same as before, ang atong vertical rugged is ang atong stiffness matrix. Okay? Now, for two-dimensional frames, nana po tayo additional degrees of freedom, no? So, we have the, di ba, sa beams na to, per node or per joint, you only have 2 degrees of freedom, di ba? So, you have the translation perpendicular to the axis of the beam and the rotation. Okay? Now, for frames, nanapod kay translation along the axis of the frame or the axis of the frame member. So, nana kay horizontal component niya or axial. Okay? So, that makes 3 degrees of freedom per node. So, per frame element, so naman kay duha ka nodes, mahimo ng 6 degrees of freedom, ang total number of degrees of freedom for a frame element. So we expect that the elemental stiffness matrix, okay, 6 by 6 na siya, no? So mo ni karon ang atong elemental stiffness matrix. This one is for frames. So kung atong balikon, sa beams na to, mao ni, no? Mao ni atong gidiscuss sa last meeting. So mao ni ang iyang stiffness matrix for beams. Okay? So 4 by 4 sa frames, mahimo na siyang 6 by 6. Now, there is also a distinct difference between a beam element and a frame element. Kaya ang frame element, there is a possibility nga ang iyang mga members dili align. In fact, it's in most cases, no? So ang member sa frame element dili siya align. So just like what we did for trusses, na napod tayo gitawag og transformation matrix. Okay? So katong himduman ninyo katong beta matrix. Okay, so we have to expect for frames, ang beta matrix na to 6 by 6 yapon kay iyang stiffness matrix 6 by 6 man, no? Okay, so just like what we did for the trusses, okay, so atong i-derive niyang iyang beta matrix. So we simply form a series of linear equations. Okay, so mao ni karon, and we can transform that in matrix form. So mao na ni ang result sa atong beta matrix. Okay? So in terms of angle theta, please take note kaning angle theta na to, this is the angle. If we go back to our diagram, so kaning theta na to, angle ni siya from the x-axis na to, global x-axis to the elemental x-axis sa atong frame, no? So mo ni siyang angle. It is positive when measured counterclockwise. Okay? So I hope I made it clear, no? So again, kanang theta is the angle from the global axis to the elemental x-axis and measured counterclockwise. Okay, so take note, your beta matrix is dependent on your theta. Okay? So as in the case of truss element, mo na yung atong global stiffness matrix, okay? We have this beta transpose times the elemental stiffness matrix in terms of its elemental coordinates times the beta matrix. Okay? So, kung imo ni siyang ipang substitute karon, you get the transpose of this beta matrix or the transformed matrix, and the elemental stiffness matrix which we have presented earlier, kani siya, mao man ni ang atong stiffness matrix in terms of its elemental coordinates. Okay? So, imo ni siyang kuhaon ang transpose sa beta, ang imong multiply nimo by the elemental stiffness matrix times the beta matrix, makuha na nimo karon. So this is now your elemental stiffness matrix in terms of the global coordinate system or simply the system stiffness matrix. Okay? Or pwede ra sa na K, dako nga K, no? So, or pwede ka butangan nimo global, pwede nimo ano, or system, no? Meaning sa terms of the global coordinate system. Okay, so 6 by 6 gyapon na siya, no? So, kung ato siyang tanahon, so it's a function of your modulus of elasticity, the area of the member, the length of the member is also a big factor, no? In getting the stiffness. C stands for the cosine. S stands for the sine of theta. Remember theta? Again, let me emphasize. Theta is the angle from the global x-axis to the elemental x-axis. Okay? So it's measured counterclockwise. So, no? S and C represent the sine and cosine angle theta between the global x-axis and the local x-axis. Positive counterclockwise. So again, kaniya, ano ang atong angle theta, no? As before, each elemental stiffness has been transformed to the global coordinate system. So muna ni karon stiffness matrix na to in terms of the global coordinate system, no? So ang purpose sa gidana para consistent ta, no? Okay? So in terms of one axis yan. Okay? That's why we have this transformation matrix. So we combine them to form the global structural stiffness matrix. So maurang yapon kada usa. After that, you combine, you reduce, you solve the displacements. Maurang gina siya, no? That's the very procedural, no? That's the whole process procedure in the analysis of structures using matrices. No? Okay. So the general procedure for solving the equations and calculating member forces is the same as described previously. Okay, so I think last meeting we discussed about the example of the beam problem. Okay, so let's proceed to this one. So this is a frame frame analysis of frame problem, no? So we are consider, no? We're going to consider the frame shown in this figure. Okay. So keeping all the units in terms of pounds and inches. So karon gihatag ning iyang mga properties, modulus of elasticity, the moment of inertia. So pareho ra tanan, ang area ay pareho ra sad tanan, no? Okay, so ang iya lang ni differ karon ang iyang length. Okay, so we have a frame. Ya duha ka siya ka element, mo na nga iyang element 1. Ya kani mo ning iyang element 2, okay? Ang length sa element 1 is 12 feet. So you multiply that by 12 force to express that in inches. This one is our length of element 2, no? So assuming this is our node 1, this is node 2, and this is node 3. So take note of this. Kaning 1, translation about the x, 2, translation about the y, and 3 is the rotation, no? So kanisya also 4, 5, 6, 7, 8, 9. No? So mingon ka og 4, so by the it should be divisible by 3, no? So mingon ka og 1, 2, 3, so that's one set. 4, 5, 6, another set, no? So you start with the translation along the x, followed by translation along the y, then after that is the rotation or the moment. Okay? So by looking at this system, no? So structure, okay, a frame composed of 2 members, no? And there are how many nodes? 3 nodes. Okay? Now remember per node, naasa tulo ka degrees of freedom. So that means ang expected size sa atong system stiffness matrix would be 9 by 9. Okay? Kaya there are a total of 9 degrees of freedom for this frame structure. Okay? So, well, giditso-ditso man niya, no? So basically, ang atong buhaton na ni for member 1, kani siya, I would like to show you program. Makita ba ninyo ang program? Really, no? Sorry. Stop share. Maybe the screen. So, the one in my right, nauni ang program, no, in Excel. So, for frames, for example, so mo ni karon ang akong elemental stiffness matrix in terms of the global coordinate. So, mora ni akong input, no? So, balik ko dire. Kani, na? Oh, so, so tanawon na to dire, no? Kani is the area, modulus of elasticity, area over L. This is the length, no? nya times c squared. Mo ni siya cosine squared, no? Mo ni ang iyang mga sine and cosine of the angle theta. No? Okay, so i-input ra ni nako din tanan. Okay, so this one is for member 2. After that, you have to combine, no? Okay. So, sa mga problem siya. Okay, but this is not the same problem nga example lang to. So, i-combine na siya. After that, you apply the boundary conditions, meaning you have to eliminate the rows and columns that corresponds to zero displacements. No? So, after that, you form the reduced stiffness matrix. No? Once you have the reduced stiffness matrix, you solve the displacements. So, simple as that. After that, once you have the displacements, masolve na sa nimo ang mga reactions. After that, the member forces. So, mora gina siya ang balik-balik, na? So, mora ning inyong buhaton, you have to kuan ra ka og program ani, no? Mora gyapon no stiffness. After that, you reduced. Seven 3.50. System, then this is the reduced, no? By applying the conditions. After that, you solve the displacements. Okay, after that, you have the global forces if you substitute. So, ingon na lang yun. So, in this case, for example, you have 3 frames na. So, tulo ka buhok. After that, you combine. So, I'd like to kanilang remembers kanina lang, no? So, let's go to the example. Okay. So, kaniya. So, let's start with element 1. Ang atong member 1 din ang length niya is 12 feet. So, in inches, 12 times 12, that's 144, no? Ang iyang E is 30,000. Ako ning copy. So, this is 30,000. 30, 1, 2, 3, 4, 5, 6. Kana. Ang iyang moment of inertia is 100. Ang area is 20. 20 at 1. Ang angle. So, ang iyang goal is, mamali ang akong node 1, no? Mamali ang node 2. Okay, so mamali ka akong local x, no? Mamali ka akong global. Mamali akong x, y. So, ang angle is kani. So, from the global x to the local x, should be 90 degrees. No? So, ibutang na ako 90 degrees. Okay? So, we have now this kani, mo ni 90 degrees akong ibutang. So, mo ni karon ang akong elemental stiffness matrix in terms of the global coordinate system. Okay? Now, let's go to element number 2. So, this is our element number 2. Okay, mo ni karon ang akong first node. This is my third node, no? So, mo ni karon ang akong local x na to, no? Ang akong global x kanima, di ba? So, unsa man na yung angle, 0, no? Wala man kay rotate na. That's basically the same, no? So, ato ning E0. So, ang E na to remains the same. 1, 1, 2, 3, 1, 2, 3. Ang A na to is also 100. Ang ato, iya, this lang gihapon. Ang length na this time is 7 feet. times 12, it should be 96. So we have to be consistent with the units, no? 7 times 12, that's 84. I have to change this to 84. The angle is 0. So manito ako elementary stiffness matrix of the global report system. Extend na ako marker sa so kay one man na lang from node 1 to 2. So kani 1, 2, 3, no? Node 2 to 4, 5, 6. So kani mag-1, 2, 3, 4, 5, 6. And then 2 is na sa di ba naman to sorry sa system 6 minutes na to. After that, let's combine. Ato siyang i-combine. So, siya kung ang dadig markers 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 1, 1. So, ulit dyan. So, I think I have to support 4.6 ani.